Before deriving our new transformation equation, let's revisit one of Newton's key assumptions. The assumption that it's most at risk, and in fact the ones that is wrong, is that simultaneity means the same thing in every frame. That if we begin with our clock synchronized and then I start to move, my clocks will remain synchronized with your clocks. We're about to see that this equation, t prime equal t, is not the correct relationship between moving clocks and stationary clock. The whole idea of simultaneity is frame dependent. Here's what I want you to imagine. We are in a lecture hall. You, a student, are sitting in the front row, which is filled with eager, attentive students, and each student in the front row has a clock. The clocks are all identical and completely reliable. You inspect these clocks carefully and make sure they all read the same time and tick at the same rate. I have an equivalent collection of clocks in my frame that are spread out relative to me in the same way as your clock. Each of your clock has a counterpart in my setup, and vice versa. I've made sure that my clocks are synchronized with each other and also with your clock. Then I, together with all my clocks, start moving relative to you and your clock. As each of my clock passes each of yours, we check each other's clocks to see if they still read the same time, and if not, how far out of whack each clock is compared to its counterpart. The answer may depend on each clock position along the line. Of course, we could ask similar question about our meter stick, such as I pass you, does my meter stick measure 1 in your coordinates? This is where Einstein made his great leap. He realized that we have to be much more careful about how we define length. Times and simultaneity. We need to think experimentally about how to synchronize the clock. But the one anchor that he held onto is the postulate that the speed of light is the same in every IRF. So again, the speed of light, same in every IRF. For that, he had to give up Newton's postulate of universal time. Instead, he found that simultaneity is relative. We will follow his logic. What exactly do we mean when we say that two clocks, let's call them A and B, are synchronized? If the two clocks are at the same location, moving with the same velocity, it should be easy to compare them and see if they read the same value of time. But even if A and B are standing still, say in your frame, but are not at the same position, checking if they are synchronized requires some thought. The problem is that light takes time to travel between A and B. So this is very important. So Einstein's strategy was to imagine a third clock, C, which is located midway between A and B. To be specific, let's imagine all three clocks being located in the front row of the lecture hall. Clock A is held by the student at the left end of the row. Clock B, so this is like this. This is the first clock. This clock A. Clock B is held by the student at the right end, and clock C is at the center of the row. This is clock C. Great care has been taken to make sure that the distance between A to C is the same as the distance from B to C. So the distance is same. At exactly the time when the A clock reaches noon, it activates a flash of light towards C. But since the velocity of light is the same for both places, and the distance they have to travel is the same, they both take the same time to get to C. I mean, when B reaches noon, it also sends flashlight to C. So, both places will take some time to reach C. But since the velocity of light is the same for both places, and the distance they have to travel is the same, they both take the same time to get to C. What we mean by saying A and B are synchronized is that the two flashes will arrive at C at exactly the same time. Of course, if they don't arrive simultaneously, so student C will conclude that A and B were not synchronized. C may then send a message to either A and B with instruction for how much to change the setting to get synchronized. So, suppose clocks A and B are synchronized in your frame. What happened in my moving frame? Let's say I'm moving to the right and I happen to reach the midpoint C just as these two flashes are emitted. But the light doesn't get to C at noon. It gets there slightly later. By the time, I've already moved a little to the right of the center. Since I'm right of center, the light ray moving from the left will reach me a little later than the light ray coming from the right. So let's say that this is where I am. The light coming from the right will meet me faster than the light coming from the left. Therefore, I conclude that your clock are not synchronized because the two light flashes reach me at two different times. Evidently, what you and I call synchronous occurring at the same time is not the same. To even that take place at the same time in your frame, take place at different times in my frame. Or at least that's what Einstein to postulate force us to accept.